Cool. So we'll start with a little bit of revision. So from last week, what were we talking about last week? What was the main topic? Yeah, we're talking about transformers. Anyone give me any types in construction? Yep. Cool. So we'll check what you guys remember. So what is the relationship between the number of turns on a transformer's primary and secondary windings, and how does this affect voltage and current? Yeah, more turns on the secondary is a step up, increased voltage, decreased current. Yeah, ratios increase proportionally to turns. Current is inversely proportional to voltage and the number of turns. If there's same, no change in voltage. If there's more on one, it's a step up or step down. Yep, very good, guys. Yeah, it all boils down to the relationship between the number of windings and the voltage level. And obviously, you guys have mentioned the inverse relationship between the current. And it can all be expressed as this formula. So the number of primary turns divided by the secondary turns is equal to the voltage in the primary divided by the voltage in the secondary, which is equal to the current in the secondary divided by the primary. So it shows that inverse relationship. And this is likely to be the formula that you guys will, one of the formulas that you guys will see when you go to sit your capstone next June, July. So yeah, that's what this formula is for. So if you see this, you know it's for figuring out current, voltage, and turns ratio and the transformer. Cool. So what is the main purpose of a current transformer or a CT? And why must the secondary winding never be left open circuit during operation? So if you only know what it's for, then just tell me what it's for. If you can think of a danger, let me know the danger. Yep, we do use it for metering. Yeah. So the main function is, yeah, we did talk about burden and accuracy. It's used for measuring current. Yes and no. So they're high voltage. Well, yeah, we do use them on the high voltage lines. Yep, mostly because we can't put a clamp meter around the high voltage lines because of jump voltages. Yes, a dangerous high voltage when left open. Yeah, so we can use CTs to do everything from measuring current on the high voltage lines, measuring high current in installations where they're going to be above 80 amps, so we can't safely measure it with a standard revenue meter. I've even used them, seen small ones used inside of domestic switchboards, so that when the laundry appliances are used, it automatically turns on a fan in the laundry to make sure that the moisture or humidity in the air is expelled out. It's a lot quite common in rental properties to use something like that to make sure that if they're going to tenant uses the laundry machine, it expels air out, and it's actually become a standard as part of some housing developments. So, like I think GJ's is one that's doing it. It's kind of their standard practice now. And if anyone's got any experience with that, let me know. But yeah, so a current transformer, it allows us to measure large currents safely by producing a small and proportional current in its secondary. Okay, the secondary must never be open circuited because the magnetic field would collapse suddenly and induce a dangerously high voltage. So yeah, there's a high voltage potential if we leave the secondary side open circuited. Cool. So why is an isolating transformer considered safer for powering equipment in damp or hazardous areas? Not safer than an RCD, but we're just saying safer than just plugging it into a normal power outlet. Yep, that's a good one. Cool. So yeah, so the isolating transformer separates the output circuit from the main earth reference, greatly reducing shock risk, especially valuable in damp or conductive environments, which is why a lot of the time we also use separated or SELV, separated extra low voltage, to power devices in damp situations, particularly in zones 1, 2, or even sometimes zone 0 for things like in spa or in pool lighting, because sometimes that's a requirement, especially if the pool is going to be used after hours. Cool. So now that we're kind of finished off the transformer section, so today we're going to start looking at capacitors and inductors, but we're going to start out with capacitors and talk about their construction and operation. So before we can understand them, we need to understand what electric charge is. The charge is a fundamental property of matter. It's what causes electrical effects and allows current to flow. So every electron has a charge. So we looked a little bit about that in atomic energy, but every electron has a charge. And so when we talk about a material having a charge, we're talking about how many extra electrons are stored in that material. So electric charge, so we measure it in coulombs. Please do not ask me where that word comes from because right now it escapes me, but I'm pretty sure it was some physicist. Jeffrey Coulomb is coming to mind. But yeah, so 1 coulomb equals the charge carried by approximately 6.24 times 10 to the 18 electrons. So 6.24 billion electrons. So when we talk about 1 coulomb, that's how many electrons we're dealing with. So instead of talking about how many electrons, we just say how many coulombs of charge. Cool. So we can then say each electron has a charge of 1.6 times 10 to the negative 19 coulombs. But again, this is kind of stuff that you don't need to know too much because out in the industry, we don't talk about how many electrons, or we talk about how much charge it has. Cool. So when charge moves through a conductor, it forms an electric current. So the electric current is the charge moving through the conductor, which is why it's important to what we do. So Does that make sense to everyone? Yeah, cool. Yeah. So you don't need to know the exact amount. Hopefully, if they ask you anything about this in the capstone, I will find whoever wrote that capstone and ask why is this relevant, other than it's a good fun fact to know. Cool. So we can figure it out using a formula. So the formula, I equals Q divided by T. So where I is the current in amperes, Q is the charge in coulombs, and time in seconds. So if 1 coulomb of charge passes through a point in 1 second, that's a current of 1 ampere. So 1 ampere is 1 coulomb passing in 1 second. So that's where we get 1 amp from. It's 1 coulomb over 1 second flowing. Cool. I know some of you guys do take notes. So yeah, this may come up. I'm not 100% sure if this will be on your formula sheet that you get given. I'm just looking at the aspect formula sheet now. And no, this is not one that is on the formula sheet. You get a different formula. So you won't need to worry about this too much. Cool. So then we can, so if we look, go back to the water analogy that we like to use. Think of a charge like the water in the pipe. The more water molecules that pass a point each second, the greater the flow. Just like more electrons means higher current. So voltage is like the water pressure pushing the flow. Cool. So if 16.5 coulombs of electric charge move past the point in a conductive material in 4 seconds, how many amperes of current has flown? So I'll give you guys the formula again. How many amperes of current have flown through this material? So 16.5 coulombs, 4.7 seconds. Yeah, sweet. So yeah, so it's 16.5 divided by 4.7, which gives us a current of 3.51 amps. So remember, we always take it to 2 decimal places. I think it's 3.5106. But if we round that 6, it becomes a 1, and we round the 1 down to a 5.1. Cool. So, but how does it work? So does anyone know how a capacitor works, or think they know how a capacitor works? Holds a charge. Does anyone know how it does it? All right, some of you, yeah, cool. So a capacitor is an electrical component designed to store a charge and then release it later. So it stores a charge. It consists of 2 conductive plates separated by an insulating dielectric material. This could be air, plastic, ceramic, etc., when we apply a voltage, electrons gather on one plate and are repelled by the other, creating an electric field between the plates. So all the electrons, basically they see the capacitor as a dead short, and so they rush to one side, but it's actually not a dead short because the dielectric, even though it's very, very thin, it still won't allow the current or the electrons to flow. So they gather on one, but they're repelled by the other plate because the other plate has become positively charged. Or it's not. It does not allow the electrons are not allowed to flow through. A lot of times you'll see the more common one is when we think of a capacitor, we think of the cylindrical caps that we see either in motors or on circuit boards. So these plates are not actually, they're not plates in the traditional sense. They're actually strips that are wound around each other in a round pattern to fit inside that capacitor. So that's how the capacitors are actually physically constructed. But yeah, that's very good. Can you please, actually it'll be in chat, I'll be able to steal that. Yeah, thank you. Yeah, everyone can just, like a spiral, so it's wound around, and so one end is connected to one leg, and then the other plate is connected to the other, thus forming a capacitor. That is the most common type you'll find out there in kind of the everyday world, because the capacitors are used for smoothing of DC, especially in power supplies. So if you were to open up the power brick for your computer, you would find a few of these in there that are used for DC smoothing. So now we've looked at the capacitor itself. Yeah, cool, Sean. I'll just leave it. So now that we've looked at how it works, we'll start looking at the next idea. So it stores a charge, but what are capacitors normally rated in? What are they rated for? So when you pick up a capacitor, it usually has a voltage rating. Close. I think you've got the right word, but you've got the wrong spelling. Yeah, Jordan's got the right spelling. So they're normally rated not in farads, because a 1 farad capacitor would be big enough to store a charge to probably quite badly hurt you. The most common you'll come across is either microfarads or sometimes even picofarads. Yeah, micro, nano, pico. Yeah, because a 1 microfarad capacitor is enough to give you quite a big wallop. So if you had a 1 farad capacitor, that'd be about the size of I think the last one I held that was 1 farad was the size of a 2 Lynx cans stacked on top of each other, just for reference. And we discharged it, and it made the loudest bang ever. It was quite frightening. So does anyone work with capacitors, and where do you find them? So where out in the wild have you guys played around with capacitors? Motors, yep, especially single phase. Heat pumps, single phase. Yep, oven, camera flash, yeah. UPSs, yep. Capacitor banks and some switch yards. Yeah, a VSD. Yep, electronics in high school. Printed circuit boards, yep. Yep, TV. Yeah, sometimes being able to solder and remove. Oh, they have them in wind turbines. Oh, yeah, that makes sense. What? A capacitor shot through the rooftop of a UPS. Far out. Like while it was working on it, or did you just see the aftermath? Oh, lodged itself in the ceiling. Wow. he screwed up? Yeah, okay. Yeah, fair enough. Yeah, everyone makes mistakes. I'll admit I've made mistakes before. You know, talking about capacitance, so you can have other things act like a capacitor. So if you have two conductors side by side, they can act like a capacitor. So when we do our insulation resistance test and we put 500 volts DC down two cables or two conductors inside of a cable, they actually act like a capacitor. So if you're not careful, the person at the other end, even if you've stopped doing your testing, can still get a zap. So I was insulation resistance testing a pair of 125 aluminium cantols for a submains out to a switchboard for an EV charger. And so I was on the phone with the other apprentice, just doing the testing. I turned off the meter. I told him, yep, I've turned off the meter. And next thing I know, he just goes, because he'd got a zap between the two cables because we had them stripped at each end for testing purposes. And so, yeah, he managed to get a bit of a zap when he handled the cables. So you can turn your electrical cables into capacitors because the plastic or the tough plastic in the cable is a dielectric or an insulator. So we can turn cables, if they're big enough, into some pretty decent capacitors. Has anyone had that happen to them? And those taking notes, are we good to move on? Cool. Sweet. Just worried how long I was going to have to. All good, Levi. Just join in and make sure you watch the rest of the video when it goes up. I'll try to get it up as soon as we finish. Cool. So the next thing we're going to talk about is the capacitance. So the capacitance is a measure of the capacitor's ability to store a charge. So this is the formula. So it's the ability of a capacitor to store charge, and it depends on the surface area of the plates, or the area of the plates, the distance between them, so the distance between the two plates, and the type of dielectric. So depending on the type of dielectric, they will have a specific value for them. There is a table. We won't get too far into this. You just basically, for the unit, I think for the assessment, you need to know how to use it. So basically, you get given the surface area of the plates, the distance between them, and the permeability, that's the word, permeability of the dielectric, then you can figure out the capacitance. But for the most part, when you do any calculations moving forward that have to do with capacitance or anything like that, you will be given more than likely be given a different, you'll be given the value of capacitance. Cool. So you can think of a capacitor as two metal plates separated by an insulator. When voltage is applied, electrons move onto one plate, giving it a negative charge, while the other plate loses electrons, making it positive. But the electrons can't move because it is an insulating material. Cool. So when we talk about the capacitance, it's a measure of how much electric charge a capacitor can store, and it's measured in farads. But again, normally you would not have a 1 farad capacitor, and unless it's inside big machinery or big kind of electrical circuits, you'd probably have, I guess in the switch yards, you guys might have them rated in farads, but for the most part, every day you'll have them in micro, nano, pico. I think I haven't seen any in millifarads yet, but that's just my experience. Cool. So this only works up to a point. If the voltage gets too high, the insulating material or the dielectric between the plates will break down. When that happens, the charge will leak or jump across the gap, and the capacitor will be damaged, and it will basically be a short circuit. But the bigger the capacitance, the more charge the capacitor can store for a given voltage. So they will be rated for certain voltages. Cool. So alternatively, the amount of charge a capacitor can hold increases as the voltage applies it increases. So it will be rated to hold a certain amount of charge at a certain voltage. But if that voltage was to increase, it would hold more charge. So you might have a capacitor that may be rated for 20 microfarads at 230 volts, but then it steps up another 10 microfarads when we get into 400 volts. It just depends on the voltage applied. Cool. So we can look at it at a different way though. Capacitance is equal to the charge divided by the voltage. So 1 farad means the capacitor will store 1 coulomb of charge for every 1 volt applied. Cool. So if we double the voltage across the capacitor, what happens to the stored charge? So it's a little bit tricky here, but we have to rearrange this formula. So if we want to find out the charge, so remember the charge is the coulombs. When we talk about charge, we're talking about Q. C is the capacitance. So to rearrange this formula, we would take the V and multiply it by C, which will give us Q, because we're trying to figure out the charge. So it would double because charge is directly proportional to voltage. Again, the formula, this is the formula you will actually be given on a working sheet. So if we increase the voltage, we increase the charge. So more voltage equals more charge. The formula makes it seem not that way, but you've got to remember that Q is the charge, C is our capacitance. So we have to rearrange that equation so it equals C times V equals Q. Because remember, we like using triangles in the electrical world. We change that formula to a triangle like we do with Ohm's law. Q, or the charge, would be at the top, and our capacitance and voltage would be down the bottom. Does that make a bit more sense to you guys? Okay, sweet. Just as long as it now makes sense to you guys, because yeah, that formula can make things a bit confusing. So, is everyone good if I move on, or is there anything you want me to go back so you can quickly take notes on? Yeah, just know we have quite a bit to cover, and obviously we're getting towards the end of the term, so I want to make sure we go over everything before you guys have your summer break before everything here shuts down. Cool. So now we go back to our water analogy. So again, voltage is, so this is what you would look at if it was a capacitor. So the pump is our voltage. So as we increase the pump, that membrane starts to stretch. So it starts to put back pressure. So if we look closer, cool. So what would happen if we were to suddenly turn the pump off? So we've built up this pressure, we've pushed with the voltage. What would happen if we turn the pump off? Yeah, we go back to neutral pressure, or so there's no taps. We've literally just taken the power away from the pump. Remember, the pump is just an impeller that pumps the water. What's going to happen? Yeah, we'd get some backflow or back pressure. So it would hold if we shut off the, yeah, it pushes back to the input. So remember, one of Newton's laws is that for every action, there is an equal and opposite reaction. So if we've put all this pressure on that membrane and then all of a sudden we take the pressure off, it's going to push back at us and it's going to give us a back pressure. So if we were to reverse the flow or make the pump go the other way, we would have that discharge back pressure that would give us an instant push. Because how quickly do you think that pump's going to go the other way? It's probably going to take a little while to spin up. Yeah, it's going to be slow. It's going to have to slow down and then go back the other way. That's basically what our capacitor does, is it gives us a little bit of extra push when we need it, when the alternating current changes. Cool. So there are some different features. So charging and discharging. So when we connect a capacitor to a DC source, the current flows and the capacitor charges. As the voltage across the capacitor rises, current gradually reduces. So once the charge builds up in the capacitor, the current stops flowing. So when it's fully charged, the capacitor blocks the DC current and behaves like an open circuit. But when we disconnect the supply, it discharges through the circuit, releasing the stored energy. So it's designed to hold a charge and then release it. So that is exactly what a capacitor is designed to do. It is designed to build up a charge until it reaches capacity, cue groans, and then discharge it when we remove the power supply. Cool. So we've talked about charging and discharging, talked about how it's built and what capacitance is. But what's the other key factor for a can someone guess what another key factor of a capacitor might be that we want to look at next? Yeah, there are capacitors that are polarized and non-polarized. We've looked about. I think you might be thinking about something else, but cool. So one other thing we need to take into account is we have this thing called the time constant. Cool. So the time constant, written as the Greek letter tau, which is basically a T, indicates how quickly a capacitor can charge or discharge. So how quickly it will build up that charge and how quickly it will release it. So that is based on T equals R times C. So where R is the resistance and C is the capacitance in farads. So depending on how much resistance is in the circuit and how much capacitance is in the circuit, or how much the capacitance of the capacitor is, will dictate how quickly our capacitor will charge and discharge. Because remember, resistance is the opposition to current flow. So the more resistance we have, the slower that current flows, the longer it takes for our capacitor to then charge and discharge. So if we increase resistance, it's going to take longer because the current has more resistance to go through. Also, if we increase the capacitance, we have more capacitance to fill up. So it's going to take longer for it to charge as well. So these are the two factors that we need to take into account when we are calculating how long it's going to take to charge and discharge our capacitor. Cool. So a capacitor is a passive component. It stores energy. It doesn't create it. In a circuit, a capacitor is usually used along with a resistor. The resistor helps to limit the flow of current going into and out of the capacitor. The resistance value of the resistor directly affects how long the capacitor takes to charge. Cool. Cool. Another factor that affects charging time is the size of the capacitor, as capacitance. A larger capacitor can hold more charge, so it takes longer to fill or charge up. So reactive is, so we're going to talk a little bit about reactance later. So what we're saying, it's passive as in it does not create energy and that it cannot create any more energy. It just stores the charge and holds it. There's no other effects at work. When they talk about reactive, they're talking about when we talk about impedance, but we will get into that later on in the session. Passive just means that it doesn't create any additional current or any additional EMFs like you would get in a transformer winding. So there's no magnetism. All it does is hold a charge and it doesn't change the type of energy. That's all it means by passive. It just sits there, takes in the charge until we're not giving it a supply, and then it gives it out. That's all it's saying when it says it's passive. Does that make sense, Sean? Sweet. Yeah, so all it's saying is for the purposes of the electrical circuit, all it does is take in a charge. It doesn't do any extra work. Basically, the charge you put in is the charge you get out. Cool. There's more info to go through. Is everyone good to move on? Cool. So they don't charge linearly. They don't charge or discharge at a steady or linear rate. Instead, they charge quickly at first and then slow down as they get closer to full capacity. This charging pattern is described using something called a time constant, which we've talked about. Which helps us calculate how long it takes to reach a certain charge level. Think back to the pipe and rubber membrane analogy. When the water first starts flowing, the membrane stretches easily, but as it fills and becomes tighter, it stretches more slowly. Capacitor behaves in the same way, fast at first, then gradually slowing down as that plate gets charged up. So the current rushes ahead into the capacitor, but then it basically, there's only so many electrons that can fit into it. So eventually it leads to a bottleneck and then eventually slows down to a stop. Kind of like when you go to a music or sporting event, you know, there's a huge crowd outside, but then all of a sudden they hit the turnstiles and then boom, gridlock, and it takes ages to get in. Yeah, it's really great when everyone tries to not get to a sporting game or a music gig too early, and then everyone comes at the last minute, and then all of a sudden jam-packed, can't get through. I'm sure a lot of you guys have had that kind of thing happen to you before. Cool. Yeah, it really doesn't help if the security guards have been told to do like full body searches or full body pat downs. That really slows things down, especially for what was it? I think it was the Netsky gig at TSB. Yeah, that slowed things down so much. Cool. So some key points to take note of if you haven't taken note of anything else. Cool. So after one time constant, the capacitor has reached about 63% of its full final voltage. So after one time constant, it already gets to 63% of the final voltage, but it takes 5 time constants or 5t for the capacitor to fully charge to 100%. So the same timing applies when discharging. So one time constant to drop to 37%. So obviously 63 and 30% are the opposite of each other when we're talking about 100%, but then it takes 5 time constants to reach 0. Does that make sense to everyone? Yeah, it's the same kind of thing when you go to like a Phoenix game at the stadium. How do they differ from a battery? So a battery will hold a much bigger charge and it will release the charge at a slower rate. So it will only release 12, it's only 12 volts, whereas a capacitor will discharge basically as soon as it can. So a battery is a cell rather than a capacitor. So a capacitor is quick charge, quick discharge, whereas a battery and a battery is normally a chemical. So a battery is normally a chemical type of storage rather than we call capacitors static charge. Capacitor, as long as you don't over voltage it, they can last quite a while. If you think of how long some capacitors last in motors and in compressors, But yeah, so a battery is a chemical device which holds a charge in its chemical makeup. So even lithium ion is still a chemical type battery. Lead acid is a chemical type battery, whereas a capacitor is based on static charge. So the surface of an area holds the charge, much like you get the static charge build up on a metal frame of a door or on the surface of a balloon. So yeah, a capacitor would be a horrible type of storage device for something like solar power, but it's very good for smoothing out DC because it will basically, as the AC rippled DC passes over the capacitor, it charges and discharges quick enough that it smooths out the DC waveform. Yeah, batteries are a chemical device. They are not a static, which is what a capacitor is. It's not a static device. Does that make sense to you, Sean, and everyone else? So yeah, chemical battery is a lot more stable and it's going to release its energy in a predictable and very steady way. Whereas a capacitor, as soon as you take the voltage off, I'm going to dump everything I have as quickly as I can. Cool. So when we talk about the discharge characteristics and time constants, so these are kind of the forms you're looking at. So if you see the charging, the voltage reading across the capacitor goes up and up and up. It stores that charge as a voltage. So remember, voltage is a measure of potential difference. So the more voltage in the capacitor, the greater potential between the capacitor and ground and earth. But obviously, as we increase the voltage, current flow drops off because it's reaching full charge or full saturation, whatever you want to look at it. But as you can see with the discharge, it's kind of opposite. But yeah. So with the charging for the voltage, we're going up to a peak. So if it's charging up to 1 volt, you can see after one time constant, we're at 0.63. So to get to half a volt, it's only taken us 0.7 time constants. And then obviously at 4 time, we're at 0.98. And then at 5, we're at full charge of 1 volt. So that is the curve. So obviously you could look at it as 230 volts if we're talking about mains power, or 400 volt, or if we're talking about rectified DC, it might be 12 or 24 volt as the top charge. And then so one time constant would be 63% of that. Yeah, that's the charging. And then obviously current's going to flow very quickly at the top, and then it's going to slow down as we reach full charge because there's not as many electrons flowing through. Sorry, pushed the wrong button. So yeah, after one time constant, we're already down to 0.37 of our current flow. So the opposite is true for the current flow in the circuit, whether we're looking at charging of the so once we're at 63% voltage, we're only at 37% of current. So there's always going to be, because remember, current and voltage for this are inversely proportional. And then if we look at the voltage discharge, again, it discharges very quickly. One time constant is 0.37 volts. But again, it is the opposite if we look at the capacitor discharge current. So after one time constant, 0.37. Yeah, cool. So if we have a 10 kilo ohm resistor and a 100 microfarad capacitor, the time constant equals 1 second. Cool. So this shows that a 10 microfarad capacitor would charge to 63% of its capacity in 1 second and will take about 5 seconds to fully charge. So T equals R times C, resistance times our capacitance. So we've put a resistor in series with a 100 microfarad capacitor. And remember, micro is times 10 to the negative 6. No. Yeah. So we move the decimal point 6 places. So we need to add 3 zeros in front of that microfarads. That makes sense to everyone, how we move the decimal place? Or is anyone confused by that? So when we're talking about milli and micro, milli is 1 millionth, and then micro is 1 billionth of a single unit. So we're talking about microfarads, it's 100 billionth of a farad. That's why we have to move the decimal place. The other way we could have done this is we could have gone 100 times 10 to the negative 6, which would have given us the same answer. So what happens to the charging speed if we increase the resistance? Yep, it will slow down and take longer because we've increased the time constant, because it's a result of the capacitance times the resistance gives us our time constant. So some summary notes. So charge, or Q, is measured in coulombs C. 1 coulomb is equal to the charge of 6.24 times 10 to the 18 electrons. Current, I, equals charge per unit time. Cool. A capacitor stores energy by building an electric field between the two plates. The rate of charging depends on both the resistance and the capacitance. And after 5 time constants, the capacitor is fully charged or discharged. Cool. So I am going to take a quick 3-minute break to give you guys time to write those down real quick. Okay, cool. So we have looked at capacitors, and now we will take a look at inductors. So what do people already know about inductors? What are inductors? Yep, that's one type. Yep. Yep, so they are typically coils of wire that use, the store energy in a magnetic field or create a magnetic field. So when we talk about inductors, we need to talk about inductance. So in the last section, we saw how capacitors store energy in an electric or static field. Inductors do the same thing, but they store energy in a magnetic field created by the flow of current. So inductance, which is represented by L, is the property of a conductor that opposes change in current. So it's measured in henries, and 1 Henry is defined as the inductance that produces a voltage of 1 volt when the current through it changes by 1 amp per second. So the inductance that will produce a voltage of 1 volt when the current through it changes by 1 ampere per second. So when current begins to flow through a coil, we get a magnetic field which expands. The lines of flux cut the coils of the inductor, causing an EMF to be induced into the coil, but in the opposite direction to the initial current flow. This acts as a pushback or back EMF to the current flowing and happens for as long as the magnetic field continues to expand. When the current stops, the magnetic field collapses back down and induces an EMF in the other direction, which is the same direction as the current flow was flowing in the first place. As the magnetic field collapses, current continues to flow in the same direction until the field has fully collapsed. Cool. So we have current in a coil, it creates the magnetic field. We get the lines of flux, which cut the coil of the conductors of the inductor itself, causing a new EMF into the coil in the opposite direction. So it opposes regular current flow. It acts as a pushback to the current, slowing it down. Happens for as long as the field continues to expand. So once it's created, it will not do anything else. So it only affects if we have a expanding and collapsing magnetic field. Cool. So once the magnetic field begins to collapse, it induces an EMF in the opposite direction, which was the same as the original current flow. It's considered to be back EMF. As the magnetic field collapses, it will continue to flow until the field has fully collapsed. Cool. So it's represented So BL equals L times DI over DT. So the induced voltage is equal to the inductance, which is measured in henries, and you have DI over DT, which is the change in current over time. So the change in current divided by time. Cool. So what would happen if the current through the coil suddenly changes? Cool. So yeah, what happens if the current through a coil suddenly changes? All of a sudden, the current has gone the other way. What happens? Sort of. So when we change the direction of the current, what happens to the magnetic field? It reverses or it starts to collapse. Yeah. So the magnetic field begins to collapse, which then induces a voltage that resists the change. So we get a back EMF. This is known as self-induction. So even when we're using a motor or a transformer, because we have this magnetic field that is being created and destroyed, it has a unfortunate side effect of having this self-induction, which opposes the change in current flow. So whenever we change the current flowing through an inductor, the voltage is induced that resists the change, and it is known as self-induction. So we've looked at a little bit of the basics of an inductor, and now we'll look at how it's constructed. So an inductor is made by winding an insulated copper wire into a coil. So specifically insulated, because if it wasn't insulated, it would just be a really big conductor rather than a inductor. It's often around a core material that concentrates the magnetic field. So a transformer, basically. The core type is what determines the inductor's strength and efficiency. So the more magnetically permeable or the less reluctance the material has, the stronger the strength of the inductors, the stronger the inductor and the more efficient it is. So similar to a transformer. So the core type will determine how good the transformer works and how efficient it is. Cool. So there are three main types. So you have your air core. It has no magnetic material and it's used in high frequency applications. So where the frequency is higher than normal. So there's an example. It has no core material. It's just wound into a coil and left like that. Then you have your iron or steel core. It increases inductance and it's used in low frequency power circuits. Cool. So it's same kind of coil but wound around an iron or steel core. And then you have a ferrite core, which is very efficient and it's common in your electronic circuits. So you might see something like this on a printed circuit board. So when we talk about low frequency power circuits, we're talking about kind of your standard 50 hertz. Whereas the high frequency applications, we're talking like switch mode power supplies or when we're converting AC to DC, sometimes we'll use an inductor as well. But yeah, applications where the frequency is above the standard 50 hertz frequency. And again, the ferrite core, you'll see that on some printed circuit boards. If you open up the power supply for your computer, if you've got a big stand computer, you'd find one of those ferrite cores in there as well. Any questions on the construction of an inductor so far? So hysteresis is about losses. So permeability is the how easy it is for the magnetic field to pass through a material. Hysteresis is the losses due to heat made by the creation and destruction of the magnetic field. So the more permeable or magnetically permeable a material, the less hysteresis loss we'll get. Sweet. Cool. So factors affecting inductance. So if a capacitor resists sudden voltage changes, an inductor resists sudden current changes. So think of it like a heavy flywheel that keeps spinning when you try to stop it and make it go the other way. Cool. So that formula there, so our inductance is equal to the number of turns squared, so more turns, greater inductance, multiplied by the core material. The core material, which increases the inductance. So the core area, so larger cross-sectional area equals greater flux linkage, and the coil length. The longer coils have less inductance. I think that alpha is the core material. So magnetic materials increase the inductance. Obviously, if we have an air core, it's not, it doesn't add anything. If anything, it would be less helpful. But obviously, if we've got a ferrite or an iron core, it's going to add to our increased inductance. Yeah, more turns we have for the less length. So the overall, so the longer coils. So it's the coil length. So how long it takes it to get from one point back around on itself. So we have longer coils, less inductance, more turns, more inductance. Cool. So how a inductor behaves in a circuit. So will an inductor have any effect on a DC circuit? Do you guys think an inductor will have any effect? Also, Timothy, your answer's not quite right there. But most of you guys seem to agree it wouldn't have any effect on it. Cool. So when we apply a DC current or DC voltage, the current starts at 0 and increases gradually as the magnetic field builds up. But once a steady current is reached, the magnetic field stabilizes and the inductor behaves like a simple conductor with very low resistance. When the power is switched off, the magnetic field collapses, inducing a voltage in the opposite direction, known as inductive kickback. But there is no overall effect on the DC circuit because there is no changing current or changing magnetic field. So once we have a magnetic field established, the inductor just behaves like a normal conductor with very low resistance. So, yes, it has a tiny effect when the DC power supply is first turned on and when it's turned off, but for the most part, it has no effect. So if we add a simple Zener or diode before our inductor, which prevents backflow or back voltage or current, then we can manage the effect. Cool. So what happens when we suddenly switch off an inductor carrying current? What do you think happens when we suddenly switch off an inductor carrying current? Yeah, we'd have the field collapse and we'd have an inductive kickback. So it tries to keep the current flowing by producing a voltage spike in the opposite direction, also known as the inductive kickback. Cool. This is why relay coils and solenoids often have diodes fitted across them to safely absorb that back voltage and protect other components. Cool. So energy storage in the inductors. So energy is stored in the magnetic field surrounding the coil while the current is flowing. So it only has the magnetic field while the current is flowing through the inductor, and that's how it stores energy. But when we stop the current, the magnetic field collapses and releases the energy back into the circuit. So it holds on to the energy for us as long as we have current flow. But then as soon as we stop putting current through it, it has a bit of a kickback, which again is why we fit diodes into DC circuits for relay coils, so that we don't have this massive kickback. So if you open up a DC relay, you will find a diode inside it to protect against this kickback. Cool. So we just talked about stored energy and supply is switched off. It's released back into the circuit, often seen as a voltage spike. Cool. So some summary points. If you haven't gotten any notes, good to get these down. So inductors store energy in a magnetic field created by the current flow. They oppose any sudden changes in the current. And when the current stops, the collapsing field induces a reverse voltage. And the magnetic energy storage is proportional to both inductance and current squared. So they're used in relays, solenoids, chokes, filters, and transformers. So the amount of energy stored is proportional both to the inductance of the coil and the current squared. So it has a exponentially proportional effect on the amount of stored energy. So obviously, those of you guys who work on the network, you deal with transformers a lot. But everyone out there, how often do you guys deal with inductors? Or where have you found inductors out in the wild? That's why I give some people a chance to note these down. Yeah, induction hobs, they're becoming a lot more common. Oh, yeah. See them on circuit boards, yeah. Yes, they are in speakers. We use them when we put a charge through it. It creates a magnetic field, which pushes the speaker cone in and out. It's basically anywhere where we make use of magnetism, you will find a inductor or a coil that creates a magnetic field. They have their DC and AC applications, but they do not have any effect on the because we don't have a change in current flow. They have more of an effect on the AC supply than the DC that we'll talk about in a little bit. Cool. Anyone need me to stay on this slide, or can I move on to the next one? Cool. So, and here's just a table breakdown of all of the different features of a capacitor versus an inductor. So you guys are aware you can push the function shift, which is function print screen, if you're using a Windows computer, which will take a screenshot of the slide. So that way you don't have to spend the entire time taking the notes down. You can quickly take a snapshot of this, but also again, it will be in the YouTube video. So you can copy it down from there. But I'm just being conscious of the time. So I think we will quickly move into the next section. Sorry, guys. So reactance. So we've looked at a little bit at DC. So now we'll take a look at how alternating currents, or AC, interacts with capacitors and inductors, creating reactance, and why direct current behaves differently. So AC versus DC. So before we understand reactance, we need to take a look at how AC and DC behave differently in a circuit. Cool. So DC flows in one constant direction. So the voltage and current will stay steady over time. Because nothing is changing, no reactance is created. Capacitors either charge and stop conducting, or inductors quickly reach a steady magnetic field and act as a short circuit. So there's very little effect when we have a DC supply. Thank you, Aaron. So yeah, so there's very little effect on a DC supply when we hook up a capacitor or an inductor to it. As long as we have a steady direct current, there will be no change in magnetic field and no chance for the capacitor to discharge. So we talk about it not having any reactance in a DC circuit. So we only worry about resistance when it comes to DC. But AC, so think of DC as the steady push of water in one direction. Nothing really changes, it's flowing. Whereas AC, it constantly changes direction and magnitude. And the continual change means the capacitors and inductors are constantly charging, discharging, or building and collapsing their magnetic field. This opposition to the change in voltage or current is what we call reactance. So AC is like pushing the water back and forth in a pipe. Every time the direction changes, components that store energy have to respond. That resistance to change is what we call the reactance. So for the capacitor, it's in the charge and discharge of it, and then for the inductor, it's the building and collapsing of the magnetic field. So this is all of the components that create reactance. So yeah, the capacitor may be considered a passive component, but it is also a reactive component. So yeah, when we talk about reactance, we're talking about capacitive and inductive reactance. Cool. Is that clear to everyone how AC and DC behave differently with these components? Cool. So in a little bit, we'll talk about how the capacitive and inductive components behave differently and have different effects on current flow. Cool. So which type of current, AC or DC, will cause reactance in a circuit and why? Yep, it's AC because it's always changing direction. So we're always going to get charging and discharging and collapsing and growing magnetic fields. Cool. So reactance. So resistance, or R, is the opposition to current flow caused by collisions of electrons within the conductor material. It converts energy into heat. Reactance, X, is opposition to current flow caused by energy storage in an electric or magnetic field. So it doesn't waste energy, it stores and releases it with every AC cycle. Cool. Reactance is measured in ohms, just like resistance. So when we talk about our resistance, it's the actual resistance in the copper in the windings inside of the actual load itself, or what we would consider the thing that's doing the work. Whereas our reactance is the charging and discharging of the capacitors and the creating and collapsing of the magnetic field. So whenever we have a piece of equipment that has inductors or capacitors inside of it, it is going to have reactance. But again, it's not a waste of energy. It is storing and releasing with every AC cycle. It's just not always in a helpful direction. Cool. And it's still expressed in ohms, just like resistance, because it is still an opposition to current flow. So it is still a opposite. Any opposition to current flow is measured in or represented in ohms. Does anyone need more time? Okay, cool. Let me know when you guys are finished. All right. While those guys are still going. So everyone knows we're coming up towards the end of the term. So we will have the end of term test on I believe the 2nd of December. Yes, Tuesday, the 2nd of December. And then that will be it for the term. And then, yeah, we'll be coming back in the new year. So obviously when we get to that, we will do the end of term test. So yeah, It will only be about stuff that we've covered this term. So about the transformers and the inductors, capacitors, and all the things we've been talking about. Yes, when we are back, so everything's available on the calendar, which I can pull up right now. Oh, yeah, I'm working up until the 15, up until the last day at work for us is the 19th of December. Yeah, I just had a crazy couple days with the current block course that we're on. But yeah, the plan is to sit down and do some marking tonight and tomorrow as well. Oh yeah, so damp situations, transformers, capacitors, inductors, and electronics. And then we are back first week, February 3rd. And if you look at the calendar for next term, the first 2 weeks are designated for block course preparation. More than likely, it will be in May, June. So similar to year one, you'll do it towards the end of next term, end of the fourth term. Actually, give me a moment. They will all be in May. Yeah. So it'll either be starting on the 4th of May or the 18th of May. It's not guaranteed which one you will be in. Yes, it is 2 weeks this year. So yeah, I'm looking at the calendar for next year, and at the moment, your block course, the 2 block courses are scheduled for the 4th of May and the 18th of May. And just like last year, it looks like I will be on pre-trade, so foundation classes, while you guys are here for block course. So you will have pretty much the same tutors you had last time, for the most part. You'll definitely have Paul, Lindsay, and Arthur. Cool. Moving back into the lesson. So some key concepts to note down. So the key concept. So reactance affects the phase relationship between voltage and current. So in inductive circuits, current lags behind the voltage. And in capacitive circuits, current leads the voltage. So if you were to draw a voltage waveform on a piece of paper, the capacitive current would be ahead of the voltage and the inductive would lag behind it. Okay. Does that make sense, or would you guys like me to quickly draw something on the whiteboard? Yeah, cool. So yeah, if anything's not clicking, just please sing out because I know sometimes I just keep going and something just gets lost. So please put something in or just turn your mic on and speak up so that way I know you guys need some extra. Cool. So put this in a little bit easy way to remember, or just remember this. Civil. CIVIL. So capacitive, current, voltage, current, inductive. So CIVIL. So C for capacitive, I for current, V for voltage, I for current, L for inductive. So always remember when it comes to reactance, civil. It's the way I was taught back when I did my apprenticeship. We kept going on about civil this and civil that. So it's just a nice, easy way to remember the relationship between voltage, current, capacitive, and inductive reactance. Yeah, so hopefully that sticks in your brain. Cool. So now that we've looked at what reactance is and how it affects the voltage and current, let's have a look at our inductive reactance. So we'll look at inductive and then capacitive. So our inductors oppose changes in current because of their magnetic field. So the faster the current alternates or the higher the frequency, the greater the opposition. This is expressed as inductive reactance. So it opposes the change. So the faster we change the current or the higher the frequency, the greater the opposition. So it's expressed in the following formula. So we have XL, or inductive reactance, is equal to 2 pi FL, or 2 times pi times the frequency times the inductance. So XL is our inductive reactance, F is the frequency, and L is the inductance. And I am not going to try and recite pi to X so many numbers. All you need to know is that there is a button that is the pi symbol on your calculator. So you just push 2 pi times, well, for New Zealand, it would be 50 hertz times whatever inductance value you're given. It's usually going to be in millihenries or small mh, because most of the time it won't be anything big enough to be a full Henry that we're working on, except obviously for you guys working out there in the transmission network. I imagine the transformers you use would be rated in multiple Henrys. Cool. This formula makes sense. Pretty straightforward. Yeah, cool. So now that we've got the formula, let's have a look at an example. So we have an inductor of 0.1 Henry or 100 millihenries, and it's connected to a 50 hertz AC supply. What would be our reactance? So we would have the XL equals 2 pi times 50 times 0.1, which will give us 31.4 ohms. Yep, it should be 0.42. 145.926. Yep, cool. So now, what if we double the frequency to 100 hertz? What would be the reactance now? Yep. So basically, we've doubled the resistance or doubled the reactance by doubling the frequency. By only doubling one thing, we've doubled the entire reactance. Yeah. So when we double the frequency, we double the reactance. Pretty straightforward, right? Sweet. We're almost at the end, guys. Cool. So think of an inductor. Remember, like we talked about the heavy flywheel in a machine. It resists sudden change in motion. So just as an inductor resists changes in current. So what would happen to the current as the frequency goes up? What do you think would happen to the current as we increase the frequency? Like a lot of people thinking increase, slower current. Now remember, when we look at Ohm's law, current is inversely proportional to resistance. So we haven't changed the supply voltage, we've just changed the supply frequency. So if we've increased the reactance, which is another form of opposition to current flow, we get a decrease in current. So we haven't increased our resistance, but because of the increased frequency, we've increased the reactance, which is a form of opposition. It's not resistance, but it is a form of opposition to current flow. Cool. So when we talk about reactance, we will eventually, I think it's either next session or the session after, we will start looking. Does everyone remember the term impedance? Or has everyone heard the term impedance? Cool. So we will talk it in more detail, but the reason we have impedance in AC circuits but not DC is because of the inductive and capacitive nature of the circuits. So a combination of the resistance and reactance will give us our impedance, but we'll look at that calculation in later lessons. But yeah, just be aware that because we've increased our reactance, we've more than likely increased our impedance. And again, we will talk about that. Just kind of giving you guys a bit of a tease. Cool. So now we'll look at our capacitive reactance. So capacitors oppose changes in voltage. So the faster the voltage alternates or higher frequency, the easier it is for the capacitor to charge and discharge. So the opposition decreases with frequency. And it is given by the following formula. So our capacitive reactance is equal to 1 over 2 pi Fc. Cool. So where Xc equals our capacitive reactance, F is equal to our frequency, and C is our capacitance. So whereas our inductive reactance was calculated with 2 pi FL, just 2 pi FL, we see that the capacitive reactance is 1 over. So if we were to increase our frequency or our capacitance, what would happen to the reactance? What do you think would happen? Just based on the formula. Yeah, we would see a decrease in our capacitive reactance because the higher the frequency, the more times that capacitor is going to charge and discharge, it's not going to get to full charge. And then the more capacitance, the more overall capacity we have to fill, it's not going to get close to full charge and full discharge. So we're going to have less reactance because of it. Cool. So if an inductor is like a flywheel that resists change in motion, a capacitor is like a spring that pushes back quickly when voltage changes, but settles easily when changes come faster. So if we take a 100 microfarad capacitor and we connect it to a 50 hertz AC supply, Xc is equal to 1 divided by 2 pi times 50 times 0.301, which gives us our 31.8 ohm reactance. Okay? But if we double the frequency to 100 hertz, what do we get then? We're taking the same scenario, except we're using a 100 microfarad capacitor. What would our reactance be now? Yep. So we would get 15.92, or the PowerPoint's decided to change it to 15.9 for easy. But yeah, so we could basically take 31.8, and we know if we double the frequency, we're going to halve our reactance. So in an inductor, if we increase the frequency, we get a higher reactance, whereas if a capacitor, we lower the frequency, we decrease, sorry, if we increase the frequency, we decrease the reactance. Cool. So it drops and the reactance halves because the frequency is doubled. Cool. So here is a quick table. So this is the last slide, so I'm just going to leave it. So while you guys are getting that down, why doesn't DC current create reactants and inductors or capacitors? But yeah, we don't have any effect or reactance on DC because the constant current will charge the capacitor, but it will not allow it to discharge. And once the magnetic field is stable, we get no back EMF, so we get no opposition to current flow, and it acts like a normal conductor. At what point might the effect of XL and XC balance each other in a circuit? So at what point would the effects of XL and XC balance each other in a circuit? Yeah, so we have 0 degrees of phase displacement. But what do you think would happen at that point? If we have balanced capacitive and inductive reactance, what could happen at that point? So we'd still have voltage, power factor of 1. Yep, someone's already reading ahead in the material. It's good to see. But what are the dangers of that? What are the dangers of a power factor of 1? Any of you guys on the network side know what happens if we get power factor of 1? Not so much current. There's something else that is affected, and so we will look at it in later lessons because we'll look at power factor. But if we get to a power factor of 1 or a balance between our capacitive and inductive components, we get what's called resonance at unity, which can lead to all kinds of nasty side effects, including the possibility of things going very, 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 very colorfully red and exploding into many pieces. So that's the danger of having a power factor of 1. The most you want to get is to like 0.95. Yeah, you're on the right path, Daniel. Yeah, so it's quite a kind of a bit of a rabbit hole to go down, but we will start to look at it in some later lessons, so that's something to look forward to. But how do you think reactance could affect the performance of a tool or appliance in a real installation? So what's the actual effect of the reactance that we might have on some of the plant or tools that we use? it'll still function. But yeah, so remember, reactance is in opposition to current flow, and it causes a lagging or leading of the current from the voltage. So what do you think might be a consequence of that? Okay, so it gets into the power factor of things, and we will talk about it in more detail in a few lessons. But basically, when we have a leading or lagging power factor, we have more current flow than what we're actually using to do the work. So we're losing some energy to creating that magnetic field or the charging and discharging of the capacitor. So we're losing energy to do the work. A lot of people refer to it as the process of doing business. So remember how we talked about the mug of beer in the earlier lesson, or the pint of beer? You've got to pay for the whole pint, but that also includes the foam. That foam is our reactance, or the cost of doing business. So we have to pay for the whole pint, but we might only get to drink 95% of it. But what if we have a really bad bartender, or in our case, a really bad power factor, and the head ends up being like almost 50%, or a power factor of 50% or 0.5? We've lost half our beer. We're paying for a whole pint, but we don't even get to drink it all. So that's what we're talking about with power factor.